A wall feels solid because your brain labels one sensation no, but zoom in and the wall is mostly space, and so are you. So why doesn't your hand drift through it like fog through a fence? What's the real rule that makes solid feel absolute? You were taught a story about solid things. A wall is solid. Your hand is solid. Two solids don't occupy the same place. End of story. But that story is already suspicious because the word solid isn't a basic ingredient of nature. It's a feeling. It's your nerves reporting a refusal. It's what your brain calls no. So what is a wall? Physically, take a tiny slice through it in your imagination. Zoom in until the paint becomes grains, until the grains become crystals, until the crystals become atoms. And then zoom in again because the atom isn't a little billiard ball. It's more like a tiny solar system rumor, a nucleus, and then mostly space. Enormous space compared to the nucleus. Empty-looking space. You've heard this line before. You are mostly empty space. People say it like it's a cute fact. It's not cute. It's a loaded gun pointed at your intuition. Because if you are mostly empty space, and the wall is mostly empty space, then why can't the emptiness pass through the emptiness? Why, when you push your hand against a wall, do you not slowly seep through it like a fog through a fence? The usual answer is because the atoms repel each other. Okay, repel how? Not by little hard shells bumping. The don't overlap rule isn't a mechanical rule like two rocks colliding. It's an electrical and quantum rule. Your electrons and the wall's electrons arrange themselves so that bringing them too close costs energy. The wall pushes back because the electromagnetic field pushes back, and because electrons are picky about sharing the same quantum state. So far fine, that explains why it's hard. But hard is not the same thing as impossible. Because in the real microscopic world, nature does something that sounds exactly like walking through a wall. It happens every day, quietly, inside matter. Alpha decay is the classic example. Inside certain nuclei, an alpha particle, a tight little bundle of 2 protons and 2 neutrons, should be trapped. The nuclear force holds it in, and outside the nucleus there's an electric barrier. The protons inside repel the alpha particle, creating a kind of hill it would need energy to climb to escape. Classically, if the alpha particle doesn't have enough energy to climb over that hill, it stays trapped forever. It's like a marble in a bowl that isn't moving fast enough to jump out. Forever means forever. But nuclei don't behave classically. The alpha particle doesn't sit at one location with one definite trajectory. It has a quantum wave associated with it, and that wave doesn't stop abruptly at the barrier. It leaks into the forbidden region, into the you don't have enough energy to be here zone. It fades exponentially like a smell through a closed door, and sometimes rarely, but not never, that leakage continues all the way through and the particle is found outside. It didn't climb over the barrier. It appeared on the other side. That is quantum tunneling. That's walking through a wall. Not metaphorically. Literally, a thing ends up where it had no classical permission to reach. And it's not just alpha decay. Tunneling is how the sun gets away with shining at all. At the temperatures in the sun's core, protons still have a hard time getting close enough to fuse because they repel electrically. Quantum tunneling gives them a cheat code, a small probability to get close enough anyway. Without that cheat, the sun would be a dim, sulking ball. Life doesn't happen. Tunneling is also inside your electronics. Some microscopes see atoms by tunneling. Tiny junctions depend on it. Nature uses this trick like it's ordinary. So now the question becomes sharper, painfully sharp. If tunneling is real, then why aren't you occasionally real in the wrong place? Why don't you, once in a great while, put your hand on the wall and by sheer bad luck have your atoms show up on the other side? Because notice the trap your intuition sets for you. You imagine you as one object, one chunk, a particle, a dot. So you think maybe the probability is small, but given enough time, shouldn't it happen? And this is where we have to be careful, because quantum mechanics does not say never. Almost nothing in quantum mechanics is never. It says probability. People hear that word and treat it like a philosophical decoration. It isn't. It's a machine, a mathematical machine that outputs how often things happen, and it's brutally honest. If the probability is 1 in a million, you'll see it. If it's 1 in a trillion, you might still see it, given a big enough factory of attempts. If it's 1 in 10 to the power of something obscene, then for all practical purposes it will never happen, even though the theory refuses to forbid it. And that's the uncomfortable idea we're building. Many things you call impossible are not forbidden by the laws. They're just so astronomically unlikely that your whole life is too short to catch even one instance. Now what exactly is the attempt when you touch a wall? At the level of a single electron, attempts happen constantly. Electrons are jiggling, vibrating, colliding, exchanging photons, redistributing. If one electron had a tiny tunneling probability to appear on the other side of some barrier, you could get tunneling currents, and you do. But you are not one electron, you are a coordinated riot of particles. Electrons bound to nuclei, nuclei bound in molecules, molecules bound in cells, cells bound in tissue, tissue bound in a body that maintains shape by constant active processes. Even what you call still is motion, thermal motion, quantum motion, everything restless. So what does it mean for you to tunnel? It would mean your whole configuration, the particular arrangement that makes you you, rather than a smear of uncorrelated debris, would have to end up on the other side. Not one electron, not one atom, all of it together in the right pattern. And the wall isn't one object either. It's another ocean of atoms, each with its own electrons, each already occupying quantum states, each already participating in the electromagnetic pushback that your skin interprets as solidity. So the real problem is not, can a particle tunnel through a barrier? That's answered, yes. The real problem is, can a macroscopic object made of an insane number of particles tunnel through another macroscopic object without being torn apart, without leaving pieces behind, without violating all the constraints that keep matter stable? Because if only a few of your atoms tunneled, you wouldn't walk through the wall, you'd just lose a few atoms into it. You wouldn't notice. You already lose atoms constantly. You shed them. You inhale and exhale them. That's not magic. Walking through the wall means something far more precise and far more demanding. The collective, coordinated tunneling of a gigantic number of particles in a way that preserves the structure. And here's the punch in the gut. Quantum mechanics does not laugh at that request. It doesn't say macroscopic things are exempt. The equations don't have a line that says human-sized objects must behave classically. The theory allows it. It just quietly assigns it a probability so close to zero that writing it down becomes an exercise in humiliation. So we're going to frame the question correctly. Not why is walking through walls impossible, but what makes the probability so absurdly small? What exactly is multiplying against you? Is it just your mass? Is it the wall's electric fields? Is it the fact that you're warm and noisy and constantly interacting with the environment? Is it that you aren't one wave but a tangled web of waves that can't stay in step? And if you had infinite time, if you leaned on a wall forever, would the universe eventually cough up the miracle? Or is there some deeper catch hiding behind the word probability? That's the problem. That's the itch. A universe that permits tunneling and still makes walls feel absolute. So let's talk about what tunneling actually costs. Not in money, in wave. Because tunneling isn't a little animal digging a secret tunnel under a fence. It's not effort. It's not courage. It's not the particle trying harder. It's the simple fact that in quantum mechanics, an object is described by a wave that spreads out. And when a wave hits a barrier, it doesn't always stop cleanly. It can leak through as a smaller wave on the other side. Keyword smaller, much smaller. And that smaller is not polite. It's usually an exponential punch in the face. Here's the brutal rule of thumb. The thicker the barrier, and the heavier the object, the faster the wave dies inside the barrier. It doesn't fade linearly. It doesn't fade like half as likely. It fades like multiply by 10 circumflex, minus something insane. If you want one piece of math, just one, this is the shape of the answer. The tunneling probability tends to look like asterisk, asterisk p tilde xp. That's something big, grows with 1. The mass of what's tunneling, 2. How wide the barrier is, 3. How forbidden the barrier is, how far below the top you are. Now why does mass matter? Because the wave associated with a heavy object is ridiculously tight. The quantum wavelength, the de Broglie wavelength, goes like hh divided by momentum. Big mass for the same everyday speed means huge momentum, which means tiny wavelength. Tiny wavelength means the wave doesn't naturally smear out across macroscopic distances. It behaves like a sharply localized thing, not because quantum mechanics changed its mind, but because the wave is so finely rippled that any spread becomes practically irrelevant. An electron, light as a whisper, has a wavelength big enough that a thin barrier is like a foggy curtain. You can get noticeable leakage. A baseball has a wavelength so absurdly small that talking about it is almost comedy. It's not that the baseball is classical, it's that the wave features are so microscopic that all the quantum weirdness averages out into the baseball goes where the baseball goes. And you're not a baseball, you're a stadium full of baseballs glued together. So take the wall. What is the barrier? At the microscopic level, the barrier is mainly electromagnetic. The electrons in your atoms and the electrons in the wall don't want to be in the same place and the same quantum states. When you push, the electron clouds rearrange and the energy shoots up fast. That sharp energy cost is effectively a barrier. Now imagine one atom from your fingertip trying to tunnel a tiny distance into the wall, say a fraction of a nanometer. Even that probability is already ridiculously small. Not zero, but small. But walking through the wall is not your fingertip atoms tunneling a fraction of a nanometer. It's your whole body's configuration moving through a macroscopic thickness, centimeters, and the tunneling probability doesn't care that you want it. It only cares about the barrier width. Every extra little slice of thickness multiplies the suppression again. Exponential means it stacks like a nightmare. So just suppose you tried to tunnel your body through a wall 1 centimeter thick. 1 centimeter is nothing in human terms, but in atomic terms it's an absurd distance. It's like asking a mosquito to tunnel through a mountain. A typical spacing between atoms and solids is about an angstrom, 10 circumflex, 10 meters. 1 centimeter is 10 circumflex, 2 meters. That is about asterisk 100 million atomic spacings, asterisk. Even if the wave dies only a little per spacing, doing it 100 million times doesn't give small, it gives done. That's the first killer, thickness. Now comes the second killer. You aren't one particle. Let's say, just to be generous, that a single atom in your body had a tunneling probability of 1 in a billion to appear on the other side of some tiny effective barrier step. 1 in a billion is already tiny, but nature does billion-scale things all the time. There are billions of atoms in a speck of dust. So you might think with enough atoms something happens, but walking through the wall isn't some atom makes it. For you to appear on the other side as you, the atoms can't tunnel independently. They have to tunnel in a coordinated way that preserves the structure. If just one atom tunnels, you don't go through the wall, you just lose one atom. If 1,000 atoms tunnel, you still don't go through the wall, you just lose 1,000 atoms, which is still nothing. You're leaking, not teleporting. To walk through, you need essentially the entire bulk of your body, let's call it n particles, to end up displaced to the other side together, and probabilities for independent requirements multiply. That's deadly. If one particle has probability p, and you need n of them to do it in the right correlated way, the rough scale becomes something like p circumflex n. And n for a human body is not a lot. It's on the order of asterisk 10 circumflex 28 atoms, asterisk 10 octillion. So even if p were unbelievably generous, say p equals 0.99999 for each atom, you still get trouble when you raise it to 10 circumflex 28. But p is not 0.99999, it's more like a decimal point followed by a depressing number of zeros. So p circumflex n becomes not just small, it becomes a number that is functionally indistinguishable from zero in any timescale the universe gives you. That's the second killer, numbers of particles. But there's a third killer, and this one is sneakier, because it's about what you even mean by your body having a single quantum wave. When physicists talk about a particle tunneling, they mean a system that can maintain a coherent quantum state across the barrier. It has a wave with a definite phase relationship, so the part of the wave on one side and the part on the other side are still the same wave, but you are not a clean, isolated quantum system. You are a hot, wet, noisy chemical factory. You are constantly interacting with the environment. Air molecules hit you, photons bounce off you, thermal vibrations shake every bond. Your body radiates infrared light like a little furnace. Your cells exchange ions. Your blood is turbulent. Every one of those interactions entangles you with the rest of the world. An entanglement has a consequence that people like to dramatize as collapse. But you don't need drama, you just need one idea. When a system is strongly interacting with its environment, the delicate quantum phase relationships that would allow one coherent wave of you get shredded. This is decoherence. Decoherence doesn't forbid quantum mechanics, it is quantum mechanics applied honestly to large systems. It's the reason macroscopic objects don't show obvious superpositions. Not because the rules change, but because the information about the state leaks into the environment so fast that the interference effects become unobservable. For tunneling through a wall as a whole body, you'd need your body's wave function to remain coherent over a distance comparable to the wall thickness. You'd need a well-defined quantum phase for the entire configuration, but in reality the wave describing you is not a single smooth object extending through space. It's a monstrously complicated entangled state with the air, the wall, the earth, the photons in the room, the thermal field. In other words, you are being measured all the time by everything. Not measured by a conscious observer, measured by physics, by interaction. And those interactions effectively keep you localized. They keep the probability cloud for your center of mass ridiculously narrow in any practical sense. They keep the world looking classical. Now there's a temptation here to say, so tunneling is impossible for big objects? Careful, it's not impossible. We've seen biggish things behave quantum mechanically when we isolate them enough. We've seen interference with molecules, buckyballs, C60 massive compared to electrons. We've made superconducting currents tunnel in Josephson junctions. In certain devices, you can get a whole collective state, millions of electrons acting together, exhibiting tunneling-like behavior, not because they're special, but because we protect them from the environment. We cool them, we isolate them, we make them quiet. So the laws do not ban macroscopic quantum effects. They just punish you for being messy, warm, and connected to everything, and you are very warm. At room temperature, your atoms are vibrating. They're not sitting still waiting for a clean quantum experiment. Thermal motion means constant random phases. It means your internal state is changing violently on microscopic timescales. That ruins the kind of long, delicate coherence you'd need for you to tunnel as one object. So now you can see the shape of the answer. To walk through a wall, you'd need 3 miracles stacked on top of each other. 1, a wave for your whole body that remains coherent across macroscopic distance. 2, a tunneling amplitude that doesn't die exponentially across the wall thickness. 3, a coordinated outcome where the entire internal structure reappears intact, not scrambled. Quantum mechanics allows each of these in principle. It never says no, never, but it assigns a probability that is so savagely small that never becomes a reasonable word for human life. And this is the part that changes how you see reality. The wall is not an absolute barrier in the laws, it's a barrier in the statistics. The universe isn't saying you may not pass, it's saying you may pass, but you will wait longer than the age of the cosmos for one successful attempt. Now the next question is the dangerous one. When we say longer than the age of the cosmos, are we exaggerating for effect, or can we actually estimate how bad it is, at least roughly using the same logic that correctly predicts alpha decay and tunneling currents? Because if we can estimate it, then impossible stops being a vibe and becomes a number. And once it's a number, your intuition doesn't get to vote anymore. So let's do the crime, let's put a number on it. Not a precise number because a human body and a real wall are complicated, but an order of magnitude estimate is enough to make your stomach drop. We'll simplify brutally. Imagine U as one object, your whole mass moving together, like a single lump. That's already generous because your body isn't rigid at the quantum level, and keeping it coherent is the hardest part. But let's pretend we somehow freeze you, isolate you, and describe your center of mass as one wave. Now imagine the wall as a barrier of thickness, L, say 1 centimeter, L, =10 circumflex 2 meters, and the height of the barrier. Think of it as the energy cost of pushing your electron clouds into the wall's electron clouds. That cost is on the scale of ordinary chemical energies, electron volts per atom. But for a whole body, the barrier in terms of center of mass motion is effectively enormous, because the wall prevents the necessary microscopic rearrangements. Again, messy. So instead of pretending we know the barrier height precisely, we'll use the one fact that makes tunneling collapse. The suppression depends strongly on mass, and distance, Even if the barrier were only modest, the mass makes the exponent gigantic. Here's the picture. The wave inside the barrier decays like an exponential. After going through distance L, it's been multiplied by something like x minus constant x L. For a heavy object, that constant is huge. For an electron through a nanometer barrier, you might get something detectable. For a human through a centimeter, you get annihilation of probability. How annihilated? Let's do a different kind of estimate that doesn't require fancy barrier physics. Think in terms of localization. Your body's center of mass wave function, in ordinary life, is incredibly localized. You are here, not spread across the room. The spread is far smaller than an atom for all practical purposes, because interactions with the environment pin you down. To tunnel through a wall, your center of mass wave function would have to have an appreciable amplitude on the other side of the wall, displaced by centimeters. That means your wave function would have to spread over centimeters. And a massive object's wave function does not spread appreciably on human timescales unless it is isolated to a ridiculous degree. The heavier it is, the slower the natural quantum spreading for a given initial localization. And meanwhile, decoherence keeps resetting the localization constantly. So you're fighting on two fronts. The wave doesn't spread to the other side. Even if it tried, the environment keeps asking, where are you now? Millions of times per second. But suppose we grant the most outrageous condition, perfect isolation, absolute vacuum, zero photons, zero gas molecules, near absolute zero. You and the wall as a sealed quantum system. Even then, tunneling is still suppressed by the mass and barrier width, and the payoff of this estimate is not it's small, it's that the resulting probability is so small that writing it in decimal form is meaningless. You end up with a number like asterisk, asterisk, p is 10 circumflex minus 10 circumflex, asterisk, asterisk, a double exponent, a number with more zeros than there are atoms in the observable universe. And once you're in that territory, it doesn't matter whether we're off by a factor of a trillion. A trillion is a rounding error in a number like that. The conclusion doesn't move. So when someone says, given infinite time, anything can happen, physics says, careful. You don't have infinite time. The universe might not have infinite time. And even if it did, you'd need the asterisk attempt rate. How many independent chances per second to be meaningful? For alpha decay, the attempt rate is enormous. The alpha particle is rattling around inside the nucleus with an effective frequency like 10 circumflex 21 attempts per second. So even a tiny probability per attempt can lead to a measurable half-life. For you tunneling through a wall, the attempt isn't happening at 10 circumflex 21 per second in any useful sense because you're not a particle bouncing in a tiny box. You're a macroscopic object pinned by continuous interaction. Your relevant attempt rate for coherent tunneling is effectively zero because coherence doesn't survive. So wait long enough doesn't rescue you. You're not buying lottery tickets, you're not even allowed into the store, and that's the deep lesson. Improbability isn't just about time. It's about the physical possibility of keeping the quantum situation intact long enough for the unlikely event to have a chance to occur. Now let's zoom out from the math and ask the question the way your brain actually cares about it. Why does the world feel so solid? Because solidity is not a fundamental substance. It is a statistical wall built out of countless quantum rules acting together. At the microscopic level, the universe is permissive. It's weirdly permissive. It allows tunneling, superpositions, particles that take every path, outcomes that only become definite when interactions force them to. At the macroscopic level, the universe becomes strict, not by new laws, but by overwhelming numbers. A wall feels absolute for the same reason a cup doesn't spontaneously reassemble after it shatters. Not because it's forbidden, but because the number of microscopic arrangements that look like shattered is astronomically larger than the number that look like perfect cup. Entropy makes the reverse practically never happen. Solidity is like that. It's an emergent certainty made from an underlying softness. You are not bouncing off a wall because matter is hard. You are bouncing off because minor electromagnetic interactions make overlap costly. Minus the Pauli exclusion principle forbids electrons from piling into the same quantum state. And the collective behavior of trillions upon trillions of particles makes the one coordinated phase-aligned miracle effectively absent from reality. But notice what this implies. It implies that your everyday world, walls, floors, tables, your own body is not the default behavior of matter. It's the average behavior. It's the high probability behavior. The universe is not built out of certainties. It's built out of rules that assign weights, and then it lets the statistics do the heavy lifting. That's why you should feel a little uneasy calling anything impossible. Not because you're going to walk through walls tomorrow, you won't, but because it means the boundary between possible and impossible is not a moral boundary, it's not a magical boundary, it's a boundary of scale, and scale is a quiet tyrant. Change the mass, and tunneling becomes common. Change the temperature, isolate the system, and quantum effects grow teeth. Change the number of particles that must coordinate, and probability collapses into a practical no. So here's the closing thought, and it's not just physics. It's a way to look at existence. You are a quantum object that has been bullied into behaving classically by the sheer noise of the world. The universe is doing quantum mechanics everywhere, all the time. But for you, for me, for walls and tables, the weirdness is buried under a mountain of interactions so deep that it might as well be another universe, and yet it's still there, underneath. The fact that you can't walk through walls is not proof that the world is simple. It's proof that the world is unbelievably, brutally consistent. If you want to keep going with this, if you want to understand not just asterisks that asterisks the world behaves, but asterisk, why asterisk, your intuition gets betrayed. Stay with this channel, because the most interesting parts of physics are exactly where impossible turns into almost never.